Okay, so then I continue on the explanation for the factor which govern the farm column behavior. So, so during the design, okay, so we need to identify all these uh, properties. For example, to gain what is the um, that what is the bearing capacity, and also the settlement. Okay, that's been improved, okay, by using the replacement methods. Okay. So factor which govern the soil column behavior. The first one is the underinsured strength of the soil. Okay. So then we need to know what is the strength of the surrounding material, okay, or the existing soil. Okay, usually for the soft soil, so the strength of the soft soil is about 25 kilopascal. Okay. So there is the definition for the strength of soft soil. Okay. So it's strength around 25 kPa. Okay. So then usually, for example, for the deep mixing methods, okay, we try to use stiffer material, okay, or stronger material. Okay. So usually it should be range in between 100 to 1,000 times greater than the existing uh, soil. Sorry, 100 to 10 to 40 times than the existing material strength. Okay. So the next is to determine the in situ lateral stress of the soil. Okay. So this can be easily determined based by knowing what is the internal friction angle. Okay. So we can determine the lateral stress by knowing the what we call as the coefficient of lateral stress from the internal friction angle. Okay. So radius stress strain characteristic of the soil. Okay. So this is used to be included in the settlement calculations. Okay. So we need to know what is the radius stress strain. Okay. So initial column dimension. Okay. Usually for to treat for the soft soil. Okay. So the range of the improvements they call as improvement area ratio. Okay. So for example, by percentage. Okay. So usually we treat the soft soil within 10 to 40% of the existing area. Okay. So that is the suggested improvement error ratio. So from there we know how number of column that we need based on the diameter. Okay. So friction angle and stress strain characteristic of the column material. Okay. So yeah, um, by knowing what is the characteristic of the column and combined with the characteristic of the soil, so then we can determine the what we call as the carrying capacity and also the settlement. Okay. So later on we will go on how to design for the soil columns methods. So this is the installation of the stone column. Okay, we have we have seen before. So I'm not sure either this is the new one or the not the same as we have seen before. Okay. Okay, that is for the stone column by Manat. Okay. So we have several international contractor. For example, Manat, Bauer, Keller. Okay, so they are very they are very uh, have a very experience, very large experience. Okay, for the ground improvements. All right. So that's for the installation of stone columns. Okay. Now we focus on the stone columns methods. Okay. So the principle of stone columns. Okay. So we look on the load transfer mechanism. Okay. So there are four types of load transfer mechanisms. Okay. So equal stress, equal strain. Okay. So the unit cell in stress concentration ratio. Okay. And the fourth one is the stress transfer. Okay. So the first one is the load transfer mechanism. Okay, they call it stress concentration ratio. Okay. The ratio of the stress on the columns, which is the sigma, delta sigma C, to that on the soil, delta sigma S, is defined as the stress concentration ratio, which is often used to describe the load transfer between the columns and the soft soil. Okay. So this is based on the equal strain rigid loading, okay, while this is based on the equal stress flexible loading. Okay, so it depends on the type of the loading, either it is a rigid or flexible. Okay, usually for rigids, okay, it gives a higher, what we call as a stress on the column, okay, while for flexible, it gives an equal between the soil and also the stress on the column. Okay. So in geotechnical analysis, there are two ideal loading and displacement condition, equal strain and equal stress. Okay. So the equal strain condition exists under rigid loading, okay, equal strain, okay, while equal stress exists under flexible loading. Okay, so the differentiate between flexible and rigid, for example, for rigid loading, they describe as a rigid footing, while for the flexible loading, it has been described like a tire pressure. Okay. So in a column reinforced subsoil, column carry a higher stress than the soil under an equal strain. Okay. Also equal settlement on the column and the soil condition due to the modulus difference between column and surrounding soil. Okay, so this is based on the higher stress, okay, on the column. Okay, the ratio of the stress on the column to the soil is defined as a stress concentration ratio, which is often used to describe the load transfer between the column and subsoil. However, under equal stress conditions, the column and the soil carry the same stress, okay, but have a different settlement. Okay, as a result, there is a differential settlement between the column and the soil. Okay, so it depends on the type of the loading. Okay, so for a rigid type of loading, so we use the equal strain. Okay, while for a flexible type of loading, we use the equal stress. Okay. However, the equal stress can contribute to the differential settlement because the soft soil have a higher settlement compared to the columns. Okay. Okay. A conservative approach is treating stone column like palm, where as in the rotational approach, the load and are distributed between the soil and stone column as a ratio, okay, stress concentration factor of a vertical stress in the stone column and the vertical stress in the soft ground. Okay, so then we have a sigma C over sigma S. Okay, so that is for the stress concentration factor. Okay, so N varies between 2 to 6, usually 3 to 4, okay, where the displacement ratio depends on the AS. Okay, so AC is over AS plus AC. Okay, so AS is the area of the soil and AC is the area of the columns. Okay, so then, okay, so this is AS over, actually it is a AS AC over AS plus AC. Okay. Okay, then we have another one is the load transfer mechanism by assuming as a unit cell. Okay. So one-dimensional unit cell with no deformations. Okay. So one-dimensional unit cell with deformations. Okay. When a one-dimensional unit cell is under an equal vertical strain condition, it has the following relationship. Okay. So vertical strain at the depth of Z is strain Z, okay, is equal to vertical stress on the column delta sigma c over constraints modulus of the column dc equal to delta sigma s vertical stress on the column over constraint modulus of the soil. Okay. So then from there we obtain the equation D, equation 2, okay, which is the stress constant ratio under 1D conditions, which is the delta sigma C over delta sigma S is equal to the constraint modulus of the column over constraint modulus of the soil. Okay. So unit cell which consists of one column and its surrounding soil is often used to analyze column reinforced soft foundations. So one-dimensional unit cell which does not allow lateral deformation of the column, for example for this one, okay, has been mostly assumed by many researchers in theoretical development and analyzed in the past. Okay. Han and Yi point out the increase of a lateral stress from the column affected the variation of the excess pore water pressure in the surrounding soil. Okay. And Castro, Sagaceta, Jiang et al. Found that unit cell allowing the column to have lateral deformation, as shown here, which is the delta H, affected the settlement and concentration rate of the column reinforced soft foundations. Therefore, the stress concentration ratio is equal to the constraint modulus ratio of the column to the soil under equal vertical strain conditions. Okay. So later on, we may look on the use of the equation 1 and equation 2. Okay. So when a unit cell under equal vertical strain conditions allow the relationship to have a lateral deformation, it has the following relationship. Okay, vertical strain at the depth of Z, okay, which is the delta sigma CZ, okay, at the depth of Z, okay, Z is the depth, okay, minus Poisson ratio times delta sigma Cx plus delta sigma Cy over EC. EC is the modulus of a column, okay, equal to soil delta sigma soil Z minus Poisson ratio plus delta sigma Sx plus delta sigma Sy over Es. Okay. So in three-dimensional, okay, the equation 4 show that the EC over Es is not similar. Okay. Therefore, the stress constant ratio for the 1D is higher than the stress constant ratio under for the 3D. Okay. Okay, so that is for the unit cell. So then we have stress concentration ratio for the third one. Sorry, unit cell. Stress distributions. Okay. stress trans. So basically this is number 3. So distribution number 3, this is number 4. Okay. So let me change it first. This is number 3. Oh, then this is number 4. Stress distribution. This is number 3. Oh, this is number 4. Okay, then for the stress distributions, okay, this is number 3, okay, load transfer mechanism number 3. Under rigid loading, the stress distributions on the column and the saw can be simplified. Okay, based on the force equilibrium, the following relationship can be established. Okay, so then we have delta sigma z, average vertical stress applied on composite foundation. Okay. So we have a delta sigma S for the soil. Okay. So AE is the influence area, also called effective or tributary area of one columns. Okay. AC is the cross-sectional area of the column. Okay. So it means that AE is the area of this minus with the AC. Okay. Means that the AE is the total area. Okay, to get only for the soil, we need to minus it with the cross-sectional area of the columns. Okay. So then plus with the delta sigma C times AC. Okay. So that is for the average vertical stress. Okay. For the composite foundations. Okay. So dividing equation 6 by AE on both sides. Okay. So then we obtain the equation 7. Okay. So equation 7 will become, basically this is AE, this is AE. Because AE is the total area. They miss the E here. Alright. So when we divide all with AE, let me put AE. Okay. So that is the AE. Okay. So then when we divide with the AE, it becomes delta sigma Z equal to delta sigma S, okay, times 1 minus AS plus delta sigma AC, sigma C times AS. AS is the area replacement ratio. Okay, where area replacement ratio is defined as the ratio of the column cross section to the influence area. Okay, so means that AS is equal to AC, area of the column, over AS, AE. Okay, so that is for the AS, AC. Okay, so that is for the AS. Okay. Okay, considering the stress concentrations ratio, delta AC over delta AS, equation 7 can be rewritten as 1 plus n minus 1 AS times delta sigma S. Okay, so that's for equation 8. Okay, now the stress on the soil is delta sigma S equal to nu delta sigma Z. Okay, which is equation 9. Okay, so from there they obtain the stress reduction factor, which is 1, okay, over 1 plus n minus 1 AS. Okay, so it means that this equation has been included in equation 9. Okay, later on they get the stress reduction factor. Okay, so equation 10 show that the stress reduction factor is less than 1, and an increase in the stress reduction ratio reduce this factor. In other words, less stress is applied on the soil. Okay, so that is for the equations for the stress reduction factor. Okay, so for the deformations, okay, assume the deformation of the column and the soil are one-dimensional and equal. So that is for the vertical strain of the column equal to vertical strain of the soil and equal to average vertical strain. Okay, so dividing equation 7 by equation 11. So we look on the equation 7. Okay. Then equivalent modulus of the composite foundation, EEQ, is equal to ES times 1 minus AS plus ECAS. Okay, so that is for the soil modulus, ES, and also for the column modulus. Okay, then equation 13 simplify the equation 12 to determine the equivalent modulus of the composite foundations. Okay, so that is the derivation based on the stress distributions. Okay. So then this is the stress transfer. Okay. What happened to the settlement on the column and settlement on the soil? Okay. So stress transfer between column and soil in the composite foundation depends on the rigidity of loading, rigidity of the column relative to soil, and the end bearing conditions. Okay, okay, this is uh, sorry. Okay, an illustration. The load transfer and deformation in column supported embankment, which is considered an intermediate condition between flexible loading and rigid loading. In this illustration, the column is relatively rigid but deformable, and the bearing layer is not firm. There exist two equal settlement plane in the system, one in the embankment field and one in the soft soil. If the embankment height is higher than the critical height, based on the field measurement, okay, reported that critical height in the embankment were in the range of 1 to 1.5 times the clear spacing of the column. Okay, based on the model and field test, okay, fields develop a relationship of the critical height with the diagonal clear spacing and the diameter of the column. Okay, due to the relative difference between the column settlement, which is the SCL here, and the soft soil settlement, SSL, the negative shear stress, often referred as negative skin frictions, develop along the column between the upper and lower equal settlement plane, but the positive shear stress develop below the lower equal settlement plane. Okay, so that is for the shear stress. The negative shear stress increase the average vertical stress here in the column and reduce the average vertical stress in soft soil, which is higher than the initial overburden stress, but lower than the average vertical stress with field surcharge. Okay, show the stress concentration ratio at a different depth. Okay, difference. The vertical stress above the column and the soil at the upper equal settlement plane are equal, while the highest stress concentration on the column exists at the lower and equal settlement plane. If the bearing layer is firm, the lower equal settlement plane will be at the top of the bearing layer. Under such condition, all the shear stress will be negative. And the above load transfer mechanism was included in a numerical model proposed by Chen. Okay, if the column is flexible, the low stress concentration occur on the column. The column will budge and less shear stress will develop between the column and the soil to a limited depth. So this is to show the stress transfer mechanism. Okay, it depends on the condition of the thickness of the field layer, okay, and the strength of the bearing layer as well. Okay. So what's been described, as I mentioned before, okay, to show that the stress transfer, okay, depends on the field and also on the bearing layer. Okay. But definitely for the stress, for the settlements, okay, a huge settlement will be happen on the soft soil, okay, and the low settlement will be happen on the column material. So then we look on the failure modes. Okay, there are several types of failure modes on the stone column type. Okay, so you may experience crushing, shear, punching, and bulging. Okay, so for example, for crushing, column may crush when the applied load is higher than the strength of the concrete column. This furthermore likely happen to relatively brittle concrete column with end bearing conditions. Okay, so this happen if the load is greater than the strength of the column. So shear, okay, so this is very common. The shear failure may happen to a granular column. So there is a common type of general shear failure. Okay. So then we have a punching. The punching failure may happen to short granular or concrete column without end bearing. Okay. So bulging are more likely happen to a granular column in soft soil within the top portion of 2 to 3 times the diameter of the columns. So usually bulging will happen at the top of the stone column when it rests in a soft soil. Okay. Okay. Several researchers investigate the column critical length below the column length does not provide any additional bearing capacity. Okay, from these studies, can confirm the critical length of flexible column must range from 4 to 6 times the column diameter. Okay, so means that uh, only on the top of the column, okay, will provide the bearing capacity, okay, which is up to 6 times of the column diameter. Okay, there will be a situation that column also experience the horizontal loads. Shear resistance or bending moment and may fail under shear bending or rotational. Shear failure may happen to granular column. Bending failure may happen to concrete column, especially when no steering post is included. Rotational may happen to short concrete column in soft soil. Rigid inclusion can be installed inside column to increase the shear bending resistance of column. Okay, so it means that to prevent from the column to fail, okay, so then we may include rigid inclusions. Okay, for example, steel reinforcement, okay, inside the soil, inside the inside the uh, column. Okay, Okay. Okay. This is for the design consideration. Okay. So for design considerations, okay, uh, first one we will look on the column properties, okay, in terms of the material, diameter, depth, and patterns. Okay. So we have two types of patterns, either square or triangular type of patterns. Okay. Each type have their own coefficients, okay, that we need to use, okay, when we do the design. Okay. Later on, we discuss on that issue. Okay. Area of improvements or area replacement ratio. Okay, then we count for the bearing capacity. Okay, settlements. How much settlement will be occur? Consolidation. How long the consolidation will be completed? Okay. For the slope design, okay, so we consider the stability. Okay. Then when it involve what we call as earthquake event, so then we count for the liquefaction. Okay. Okay, so suitability of the backfill material. Okay. So this is how to count for the suitability of backfill material, okay, for the stone column. Okay, develop a rating system for suitability of a backfill material for fibro replacement. Okay, so SN is a suitability number. Okay. So then, for example, if we have a filling material, okay, so then we need to carry out for the particle size distributions. From there, okay, we need to know what is the particle size, okay, for each 50%, 20%, and 10% final, okay, then include in the suitability number equations. Okay. So if the value is between 0 to 10, okay, so this is a very excellent material, okay, for the backfill. Okay. So, and when you go to 10 to 20, it is good, okay, fair, poor, and if greater than 50, it is unsuitable. Okay. So then we need to play around with the equations, with the uh, particle size. Okay. Okay. So this is for the column pattern. Okay. So we have the square, triangular, okay, and radial. Okay. The common type of column pattern is square and triangular. So radial is not uh, commonly being used. Okay. But radial is more suitable for circular or ring formation like tank. Okay. So then we have there S1, S2. S1 and S2 is the spacing, okay, between one center to center of the each columns. Okay. So AS is the area of the treated soil. AC is the area of the column. Okay. So for the square, okay, that is the AS. Okay. And also for the triangular, that is the AS. Okay. Then we go for the diameter of the column. Okay. It is based on the column type. Okay. For example, for the sand compaction column, okay, the diameter is 0.6 to 0.8 meter. Okay, for the stone column, the maximum is 1.2. For the ramp aggregate column, is 0.9. So vibro concrete column, okay, it depends on the shaft and base. Okay, the maximum for the shaft is 0.6 and 0.9 for the base. Control modulus stiffness column is 0.5. Geosynthetic encased column 0.9. The maximum of the column diameter. Okay. So then for the area replacement ratio, area replacement ratio is defined as the ratio of the cross-sectional area of the column to the tributary area of the column So then we have the AS, area replacement ratio. Okay. Cross-sectional area of the column, AC. Okay. So AE is the tributary area of the column. Okay. Or we can use another equation, which is depends on the C. BC is the diameter of the column. S is the spacing, okay, center to center, to get the AS value. Okay. So for this case, C, it depends on the arrangements of the column. For example, if you use a square patterns, so the AC is 0.785, or if you use the equilateral triangular pattern, the C is 0.907. Okay. So that is for the, either we want to use the AC over AE, or we use the diameter and spacing, then we multiply with the C. Okay. So don't worry, during your final or test, for example, you are given with all this value. Yep. Okay, for the common type of area displacement ratio, okay, as I mentioned before, it is range between 10 to 40%. Okay. Let's say if we use a geosynthetic encased granular column, the AS is around 10 to 20%. Okay. With the use of concrete column, the AS is around 0.05 to 0.15. Okay. Based on the cross-sectional area of the column shaft. Okay. So that is a typical range of area replacement ratio for the stone columns. Okay. So depth of improvement, okay, that is for the area improvement. So now we go for the depth of improvement. So it depends on the site conditions, soil properties, performance requirement. Okay. When a firm stratum exists at the relatively shallow depth, the depth of improvement should reach this stratum. Okay. So it depends on the firm stratum exists. Okay. So if it's a shallow, then we go up to the firm stratum. Okay, when a firm stratum exists at the relatively deep depth, the depth of improvement should be determined to meet performance requirements such as bearing capacity, settlement, slope stability, and liquefactions. Okay, so then we need to know how to count for the capacity based on the load applied on the treated area. Okay. So typical depth of the improvement range from 5 to 15 meter deep. Okay. Let's say if the load doesn't reach, the capacity doesn't reach the load from the superstructure, although we have designed for 15-meter deep, so then we need to use another method of improvement. Okay. So that is for the depth of improvements. Okay. So area improvement, the area of improvement should be determined based on the site condition, importance of superstructure. In general, the area of improvement should be larger than the footprint of footing. Under general conditions, one or two row of column may be installed outside of the footing. On a liquefable soil site, two or four row of column may be installed outside of the footing. Okay, so let's say this is the footing. So then we need to enlarge what we call as the area underneath the footing to be treated with a stone columns. Okay, now we go for the bearing capacity. Okay. So to estimate the ultimate bearing capacity of an individual stone column in saturated soil under an undrained conditions, okay, assumption made. The interface between the column and the soil is smooth. Okay. No circumferential stress exists. No self-weight is considered for the column and the soil. Okay, so there is three assumption made. Okay, to estimate what we call as the bearing capacity of a stone column. Okay, so to begin with, okay, the equation shown here, okay, to determine what is the lateral stress from the surrounding soil. Okay, so then we include what is the vertical stress on the soil, okay, which is the delta sigma s. Okay, so undrained shear strength of the soil, okay, then the passive failure plane angle within the column, and the failure plane angle within the soil. Okay, so friction angle of the column. Okay. Okay, so that is the equation used to determine the lateral stress from the surrounding soil. Okay, so then considering the passive shear failure of the column, okay, so delta sigma C is equal to uh, sigma R times Kp, okay, the passive earth pressure coefficient, okay, as sigma R change with the failure plane angle, the maximum lateral resistance can be solved by determining the critical angle. Okay. If the vertical stress on the surface is equal to 0, then the tangent, what we call this one, let me psi. Okay, there is psi. This one is called as a psi. P S I. So that is a psi. So this is psi. This is psi for the soil. This is psi for the column. Okay. So psi for the column is equal to negative psi tangent psi over tangent to psi minus tangent psi column over tangent to psi minus tangent psi column over sine psi. So if vertical stress on the surrounding soil is equal to 0, okay, so then the tangent psi of the column is equal to half tangent psi tangent square psi minus 1. Okay. Okay. So then, okay, so I'm not sure why they come up with this approach. Okay, but later on, this is the common type of bearing capacity equation. Okay, so we have four equation to estimate the bearing capacity. Okay, the first one from the Brown. Okay, where the Q ultimate is equal to 20.75 CU. Okay. So then the other researcher, okay, estimate the capacity based on the uh, okay, so means that this equation, other researcher, sorry, is related to the sigma R. Okay. Okay, this is sigma R now. Okay, but it's not common to be used. Okay. So then we have a method from where they use similar like Brown, which is 20 CU. Okay, the ultimate on individual stone column. Okay, so since it's recommended that since granular column and the surroundings are mobilized their strength at a similar strength level, the ultimate bearing capacity of a granular column reinforced composite foundation can be determined, okay, based on this equation. Okay, so Q ultimate of the column times improvement area plus Q ultimate of the soil times 1 minus improvement area. So then we obtain the ultimate of composite soil. Okay. So from there, Q ultimate of the soil is the ultimate bearing capacity of the surrounding soil, which is can be estimated as 5 Cu as suggested by Buckdales. Okay, so once we know what is the undrained shear strength of the soil, okay, so we multiply with 5. Okay, or the easy way is the use of the 20 times Cu. Okay, so that is for the bearing capacity. Okay, so then we may use this equation to determine the capacity. Okay, now we look on the settlement. Okay, so I need to erase this one. So this is this is for the bearing capacity. Okay, now this is for the settlement. The settlement of a natural foundation under a large loading. Okay, the width of the loading area is at least 3 times the thickness of the soil. Okay. Okay, how to determine what is determine uh, the settlement? Okay, for the stone column. Okay, so the first thing is to know what is the settlement of the existing soil. Okay, so this is the equation used to estimate the settlement of the existing soil. Okay, so for this approach, we may use the coefficient of volume compressibility, okay, MV, okay. S is for the soil, okay, so that is the MV. Okay, delta sigma Z is the increment of stress, okay, at a certain depth. H is the thickness of the soil layer. Okay. So then, to determine the MV, okay, so we have two options there. The first one is the use of the DS, initial work ratio of the soil, okay, and the other one is the use of the ratio from the Poisson ratio over the elastic modulus of the soil. Okay. So this is the Poisson ratio and this is the elastic modulus of the soil. Okay. So if we are given with the Poisson ratio and elastic modulus of the soil, so we can determine the MV. Okay. Or if you are given with the Watt ratio, okay, effective stress, which is the unit width times height or thickness, and CC, which is the compression index. So we also can get what is the MV, okay, which is the inverse of ds. Okay, so near the ground surface, the soil is slightly over-consolidated. Under such a condition, the recomposition index should be used instead of CC if the total settlement is less than the pre-consolidation stress. Okay. So if it is over-consolidated, then we should change to CR, not the use of CC to get the DS. Okay. So it depends on the condition, total stress is less than the pre-consolidation. Okay. So that will be more explanations. Okay. If you want to concentrate on that issue only. Okay. So the easy way is the use of the Poisson ratio. Okay. So when the loading light area is relatively small, the width of the loading area is less than the 3 times the thickness of the soil. So then we may use these equations. Okay. So this is based on what we call as the elastic settlement equation. Okay. So P is the load, BF is the width of the footing, 1 minus Poisson ratio square over ES, I is the influence factor. Okay. So there is a table to what we call as to estimate the IS value or the I value. Okay. So then it depends on the width over the thickness of the soft soil. Okay. Okay. So it depends on the condition. Okay. So if the width of the area, for example, usually for embankment is very wide. Okay. And compared to the thickness of the soft soil. Okay. So then we may use the first equation. Okay. Let's say if we construct for a building, okay, usually the width is to is not wide, okay. Then the thickness is greater than the width of the building. So then we use the second equation. Okay. So usually when we construct for the embankment, okay, it's better to use the first approach. Okay. So then we start to estimate the settlement, okay, due to the composite foundation, okay, based on the compression of the soil, okay. So by using the stress reduction factor, okay, so we can estimate what is the settlements, okay. So coefficient of volume compressibility of soil after column installations, okay. The settlement ratio of the composite foundation to the natural foundations. Okay. So what we the prime is used to differentiate between before and after the composites, after the installation of the columns. Okay. So S prime is the coefficient of body conformity of the soil, the settlement of the composites. Okay. So for soft soil, their coefficient of volume conformity before and after column installation do not change much. Okay. Assume MVS is equal to MVS. M prime VS is equal to MVS. Okay. So from there, we can estimate what is the settlement after the installation of the composite foundations. Okay. But before that, we need to know what is the S value from the natural soil. Okay. Okay. So this is to determine the N, okay, from this equation. Okay, how to get the N value here. So the N value is equal to 1 plus 0.217. Okay. EC is the modulus of the column. ES is the modulus of the soil. Okay, minus 1. Okay. So this is what we call as approach, okay, by Bartlett and batches develop an empirical design as shown in 5.14 here of in this figure to determine the stress concentration, which can be approximate as follow the average ratio. Okay. So based on the field data, okay, the modulus ratio should be limited to 20. Okay. The typical stress concentration ratio for granular collar under range from 2 to 4. However, the under embankment range from 1 to 2. Okay. Either you want to use this equation or you can base on this what we call as this graph, okay, to estimate the stress concentration ratio. Okay. So once we determine the N, so then we put in the above equation. Okay. So Pratt proposed a basic improvement factor method to calculate settlement of stone column reinforced soft foundation by a vibro replacement method considering rigid and incompressible column with a bulging over the column length. Okay. So improvement factor IF, okay, friction angle of the column material. Okay. So AS is the area replacement ratio. Okay. Okay. Among all the preceding method, okay, Pratt is still the favorable method to estimate the settlement of column reinforced soft column in practice. Okay. So, for example, okay, we have several range of or several lines based on the friction angle. Okay, let's say our area replacement ratio is 20%. Then we go to meet which friction angle. Okay, from there we determine the improvement factor. Okay. Or we can use the equation here to get the IF. Okay. So 1 over IF, okay, is the settlement, okay, coefficient. Okay. From there, we may multiply with the S value, okay, to get the actual or to get the S prime value. Okay. So I repeat again, okay. S prime is equal to 1 over IF. Okay. So once we obtain the value for the S prime, okay, the value should be multiplied with the S, okay, to get the settlement of the material. Okay. So then to estimate the consolidations, okay, the Terzaghi one-dimensional solution can be used for the vertical flow, while the Barron solution can be used for the radial flow. Okay, so it is similar like a prefabricated vertical drain. Okay, so we have vertical and radial flow. Okay, so then to estimate how long the process of consolidations, and so you need to differentiate. Settlement is the magnitudes of deform, while consolidation is the process. Okay, so the consolidation we justify based on time, okay, while the settlement based on the displacement, okay, of meter or millimeter. Okay. Hanya ini develops in prepared solution for concentration rate of a free draining stone column reinforced soft foundation. Okay. The excess pore water pressure in the soil soft soil dissipate due to vertical and radial drainage. When the water reach the free draining stone column, it's assumed to dissipate immediately. So it is also assumed that the stone column and the soil deform one-dimensionally at the same strain. So how to estimate the consolidations? Okay. Okay. First, we need to determine the permeability, okay, the K value. Okay. Han used the formula for permeability for granular drain. We should find content in the FHWA highway drainage design to estimate the permeability of a granular column. Okay. So K value, okay, can be determined, okay, based on this equation. Okay. So 2.19 times the effective grain size corresponding to 10% passing the sieve size. Okay. NP is the porosity of the stone column. Okay, dry unit weight of the stone column times with unit weight of water times specific gravity. Okay, unit weight of water is better to use 10. Okay, or if you want to use 9.81, it's okay. Okay, but you need to consistently use 9.81 to out the whole solutions in your for example, in your assignment or uh, in your final, for example. Okay. So percentage of particle passing, okay, then power by 0.957. Okay. So all of this information will be given, okay, for you to get the key value. Okay. But you need to know to use the value. Okay. And the value should be, and the magnitude is meter per second. Okay. All right. So that is for the key. Okay. Okay, then degree of consolidations. Okay. So this is part of calculation. Okay. To determine the degree of consolidation. Okay. So for granular column reinforced foundation, so the modified coefficient of consolidation of subsoil in vertical direction, CVM, this is V is represent the vertical, can be used to calculate the time factor for Terzaghi solution for the degree of one-dimensional consolidations. Okay. So how to get the CVM? Okay. So CV is a coefficient consolidation of subsoil in the vertical direction. Okay, ND is the diameter ratio. Define the ratio of the influence diameter to the column diameter. Okay, so ND is the diameter ratio. Okay. Okay, then the modified coefficient of consolidation of subsoil in radial direction, which is the CRM, okay, can be used to calculate the time factor for barren solutions for the degree of radial consolidation, okay, TRM. Okay, so CRM, okay, that is the equation there. Okay, then from there we determine this. We need to get the CR first. Okay, CV we can get from the coefficient of consolidation. CR we determine from the KR over gamma WMB for the soil. Okay. So ND is the diameter ratio. Okay, defined as the ratio of the influence diameter DE to the column diameter DC. Means that ND is the DE over DC. Okay. Or we can use another equation, which is CR times 1 plus N AS over 1 minus AS. So N is determined from this equation. Okay. So that is for the CVM, CRM. Okay. So from there we can work out to determine the UV. Okay. Terzaghi suggested the following approximate ratio for degree of consolidation under one-dimensional vertical flow. Suggested the following approximate relationship for degree of consolidation under one-dimensional vertical flow. Okay. So then this is the typical equation for the UV. Okay. So we may use this equation, okay, when we deal with the UV to get the TV, okay, to get the TV, okay. It depends on the TV value. Okay, for example, this is once we obtain the TV value from this CVM, okay, so then we put the TV inside the equation, then get the UV. Okay, so if the UV is range between 0 to 2.6, so then we use the the means that this is the right equation to be used. Okay, if we calculate that the TV is greater than 52.6, so then we need to change from this equation to this equation. Okay, so that is for the to get the UV. Okay, so later on to get the UR, okay, so UR is little bit longer, okay, in terms of the equation. Okay, so this is the equation for the UR, okay. So then we need to use the FND, okay, to get the UR, okay, value, okay. And also the FN, okay, to get the UR value. So it depends on the TRM TRM value from here. So once we obtain the UR and UV, we can get the UVR. Okay, so the UVR is the overall degree of concentration of soil due to vertical and radial flow. Okay, so that is the final product of the degree of consolidation. Okay, based from the what we call as from the stone column installation. So once we obtain the UVR, okay, we multiply it with the S from the coefficient from the settlements that we obtain from the soil. Okay. Okay. So, okay, this is the design procedure for the stone column. Okay. So they have 7 steps. Okay. So you need to know how to you need to know on this procedure. Okay. So based on the undrained shear strength of the constitutive soil, calculate the ultimate bearing capacity of natural soil. Okay. Based on the undrained shear strength of the constitutive soil, calculate the ultimate bearing of individual column. Okay. Calculate the ultimate bearing capacity of composite foundation by considering ultimate bearing capacity of natural soil and individual column and the area replacement ratio. So based on the coefficient of volumetric compressibility, calculate the settlement of natural soil. So based on the column soil modulus ratio of the friction angle, calculate the stress reduction factor of the improvement factor, and then calculate settlement of composite foundation. The degree of consolidation of composite foundation can be estimated using Han and Lee solution considering wear resistant. In this calculation, the vulnerability of the column should be estimated first, possibly using the FHWA highway drainage method. So the fact safety against global slope failure can be calculated using the individual column method when the equivalent area method is used for undrained. The reduction factor of 0.9 should be applied to calculate with. The 7 is only for the slope issue. However, we will not touch on the slope. Okay, we only discuss on bearing capacity and also on the settlement. Okay. So that is for the design procedure for the stone column, for the bearing capacity, and also for the settlement. Okay. So we take a rest for 15 minutes before we continue for the example. All right. Okay. So we discuss on the PDF file that I give it to you on the equation and on the example. Okay. So take a rest for 15 minutes.